Hello guys, so we are going to start today force on dielectric. This is part, the last part of basically dielectrics, the various mediums we are studying in case of capacitance. So we have already studied that in a parallel plate capacitor, if there is a dielectric inserted like this, which is completely filled into it, I am just showing a gap just to demarcate the dielectric. So in that case there will be negative charges of the dielectric like this, and here there will be positive charges of the dielectrics like this. Okay, and as the plates are having positive charges on the top one and the negative charges on the bottom surface, so there will be a attractive force on the dielectric like this, and there will be attractive force on the dielectric like this. So here the force gets cancelled. However, the problem, so this is basically, before I go into the problem, this is basically the case when dielectric is completely inserted. Completely inserted. This is the case. However, if the dielectric is not completely inserted, let us take that case also. So again we will draw a parallel plate capacitor in which, let's say, the dielectric is inserted up to this part, that is not completely inserted. Yes, so this is the condition of the dielectric. Here there is negative charge and here there is positive charges. Okay, so now if you see, the force will not be exactly perpendicular to the dielectric surface. The force will be like this way. You see, the overall force will be like this one. Here also will be like this one. So in this case, definitely the forces will not get cancelled. Why? Because if you do the component of this forces, one part will be like this and here also one part will be like this, right? So these two forces is going to get added. So here will be set, say if this is f dash cos theta, and here also you will have, if this is also f dash cos theta. So here there is a net force, unlike the previous course, right? In previous case there is no net force, here there is a net force. So we can write, here there is a net force. Okay, when what is the case? Case is dielectric not inserted completely. Okay, so that is cool, I guess. So makes us think and do something else, right? So what about this case? So if I now try to break down this case, then this case is like this. So directly I cannot find out that force, but definitely indirectly I can get this force. How is it? Let's see. So here the dielectric is not completely inserted, so I'll take that maybe the dielectric is inserted up to this length. Okay, so here there is dielectric, here there is dielectric. Okay, cool. So this is having a dielectric constant as K, and this is having no dielectric constant, but that is means it's air basically. So this length is x and this one I'll take, if the total length is L, then this one I can say this is L minus X. Okay, and the width of this parallel plate capacitor is D. Okay, and there will be another dimension. Definitely you can understand the dimension on the, say, Z axis is P. Okay, so if you notice, so if this is the positive plate and if this is the negative plate, then the charge will be flowing from this side and the charge will be going out from this side. So there will be a division of charges, and here the mediums of the dielectric is different, so it will act as a parallel combination between two capacitors. So in parallel combination we know it will be C is equal to C1 plus C2. So what is C1? C1 is K epsilon naught B into X. Okay, so B is the width, the area. So to calculate the area, the width over here is B into X, that will give the area of the plate. Okay, divided by D. Okay, understood this much? I think there is no problem with this one, right? Everybody has understood. Okay, so now let us go for the other part, now L minus X part, that is the C2. So in case of that one, there will be no K, right? There will be no K, epsilon naught L minus X into B divided by the width is same. If you notice, the width is same, so I write D. Okay, so now what I'll do is I'll take something common. So from here I can take B epsilon naught by D as common. So here we will be left with Kx, here we will have plus L minus X. Okay, so what we have got over here, we have got B epsilon naught by D into K minus 1 X plus L, right? Okay, so this is the total capacity of this capacitor when the dielectric is not inserted completely. Okay, so one part we have been able to do. Now how does it help us? It helps us to calculate the potential energy of this capacitor, because we know the capacitor potential energy is half C into V square. Now that we already have C, so it becomes very easy for us to find out the other parts. How it is? Because we have got half, and the C part I can write it down, but I'll write first V square because V square is going to get multiplied, and the rest part I'll write in the bracket. Okay, K minus 1 X plus L B epsilon naught D. So this will be B epsilon naught D epsilon naught V square by 2D. Here it will be plus L. Okay, so now we are clear with the energy part, and as we know, whenever we get the energy, it becomes very easy for us to find out the force. Why? Because we use a very simple formula which is called, I'll just have a copy of this to the next slide, that will help us. Now how am I going to go to force now? So what we'll do is force is equal to minus du dx, very well known. So now you just have to differentiate this. So minus half b epsilon naught by d v square, okay, that is common. The rest part will be over here, only k minus 1, L is a constant term, so it is going to go to hell at this point of time. So if I want to find out the magnitude of the force, then it will be only half b epsilon naught d k minus 1 v square. Okay, so now we have got the force on the dielectric in a partially inserted in a capacitor, parallel plate capacitor. Okay, now next is we are going to find out what is the work done in completely inserting the slab. Now we know the force, right? So we are going to find out work done for inserting slab. So one thing is good, if you see this force, this does not depend on how much length you have entered, because you have entered over here a length of x, but see, the force does not depend on that. So work done is equal to force into the total distance that you are inserting, that is L. So this is a pretty easy one, half b epsilon naught by d, another L will come over here, k minus 1 into v square. Okay, so this one can also be written as, if you see, just trying to do something, this b into L, let us notice this b into L is the area of the capacitor, and this d is the width, correct, into v square to k minus 1. Now this formula is very well known to us. So this formula is half c v square k minus 1. So this is the formula for work done when you have to insert a dielectric into the parallel plate capacitor. So I hope this is clear. This is not a problem for you guys. So now we can go for the next part. Okay, this could have been found out by other ways also. So we can show that one also. So I'll show that one also. How do you find out this one? See, this work done, I just found out the equation of work done. So I'll again take a copy of this for the next slide, just to compare that how can I get this in another way and also compare it. Okay, so let's say this, we know that work done is nothing but change in potential energy, correct? So see, it is minus half cv square is the potential energy, but when dielectric is inserted, we have already done this, it becomes half k cv square. So this way also you can easily find out the same work done that you have done right now. Okay, just for comparison purpose I did this, need not be done again, just for comparison purpose. Now we'll do one thing, we'll understand another thing. What if the capacitor is connected to a battery. Okay, we'll do that. Capacitor connected to a battery, one by one. So the potential difference of the battery over here is V, it's given. Now what is work done by the battery? What is work done by the battery? Charge supplied into V, we know that. And what is charge supplied? We already did this. This is kCV minus CV, right, into V. So this amounts to K minus 1 CV square. Now if I want to find out what is the heat lost in this system, already done this many times, but you can again find it out. This is work done by the battery minus change in potential energy. So what is work done by the battery? Work done by the battery is K minus 1 CV square. And what is change in potential energy? We have already found out this one. So half K minus 1 CV square. So this will be at the end of the day half K minus 1 CV square. Okay, this is when the dielectric is inside the capacitor. Okay, so I think everything is clear at this point of time. Up to this, we'll end this session with a very nice problem which combines SHM with capacitance, and so that you guys can gain some confidence on whatever we have studied, and also revise a little bit of SHM chapter. Okay. Okay. So here there is a circuit. Let's draw this one. Okay. So this parallel placed capacitor, as you can see over here, is having a length of L. A dielectric is inserted into it. It is having a breadth on the Z axis as B, and the width of this capacitor is D. Okay, with this dielectric slab that is inserted in the capacitor, there is a spring attached which is connected to a rigid support. Okay, so there are two questions over here. One is battery is disconnected, another is battery is not disconnected. So that is, there are two questions. When battery is connected, that is, this is the condition, battery is connected, in that time will there be any SHM, yes or no? So let us find this out. When this dielectric is inserted into it, so definitely the electrostatic force of attraction between dielectric and the plates should be equal to the spring force, that is Kx. This is at equilibrium. Okay, so we have already calculated this force, so this will not be a very much difficult thing for us. So this force is nothing but half B epsilon 0 by d k minus 1 v square. Okay, so this is equal to kx, or you can say this is equal to the force. So if you think this is the force, you can clearly see that this total term, as I have already said, is independent of x. So no SHM. Okay, so if this force was dependent on x, then there should be a term that would have been written as x over here, but this was never like that, so it will never be dependent on x, and hence it is not an SHM. What happens if the battery is disconnected? If the battery is disconnected, so see, if the battery is disconnected, you cannot use this v square formula. You can use this one. You know that U is equal to the stored potential energy I am talking about, Q square by 2C. Now in this same derivation that we did today, we also find out the capacity of the capacitor with dielectric entered into it, or dielectric inside it. So E naught B by D, and that was, I think, k minus 1 x plus L. Okay, so now what is F? F is du dx is equal to q square d k minus 1 to epsilon b L minus x plus kx, right? L minus x plus kx. Okay, so here if you see, this is dependent on x. Yes, you can say that yes, f is dependent on x, but that is dependent on 1 by x. So here f is not proportional to x, hence no SHM. Nice problem to end our session today. I hope each and everything is clear. I taught this a little slowly. Thank you very much, each and everyone. Let us meet for the next session.